And this begins EE 544 on Thursday, April 10th, 2014.
Thank you very much. Good afternoon, everybody. Let's continue our discussion from last time. We started last time looking at different topologies or different architectures for the low noise amplifier. And again, as I told you, we were interested in three issues. What are the three parameters that we were interested in? We were interested in what? In the gain of the low noise amplifier. We were also interested in the what? In the power match. Power match means what? Impedance match, maximum power transfer. And we were also interested in the what? In the noise figure. Clear? One of the first dilemma that we faced is the following, is that if we use a common source amplifier, we already know that the input impedance of a common source amplifier is highly what? Capacitive. That capacitor is called what? The CGS, between the gate and the what? The source, highly capacitive. And if the input impedance is a capacitive impedance, there is no way that I can what? That I can match it to a what? To a real resistance. A real resistance being what? Being the 50 ohm coming from the source. Clear? Either from the feeder cable or from a filter in there. So the first architecture that we decided on is to what? Is to use a shunt resistor, which is what? Between the gate and the what? And the source. And we said what? What did we say? We said that if we assume that we are operating at a what? At a low frequency, which is the first thing to do is, the first assumption is not really a realistic assumption. Why? Because we are dealing with RF. RF has high frequencies, but we assume that, assuming that the frequency is what? Is low, the input impedance if you look at the what? If you look at the impedance between these two ports, what you will see only what? R in parallel with something which is what? Which is of high impedance. Are you following? So we end up with just R. So if we make R equal to RS, we achieved what? We achieved the maximum power transfer. It was very simple solution, and it's workable solution. It's a workable solution. But what did we end up with? When we did, first of all, the gain calculations, we ended up with a what? With a dilemma here. We found that the voltage gain was equal to minus GM. Minus, by the way, is because what? This is a common source. A common source will introduce 180-degree phase shift between the input and the output. So we found that AV equal to what? V naught over Vs, and that was equal to what? Minus GM RL over 2. Now, if I remove the R, then the gain would have been what? Minus GM RL, which means right away I say what? I say that the gain was divided in what? Was halved. Was divided in half. Was divided by 2. Clear? Now, you might say, so what is the big deal? What is the big deal is that, first of all, we need a gain to be adequate because the received signal is what? Is weak. And second, we need the gain to be adequate to reduce the effect of the noise introduced by the subsequent stages. If you remember, this is the equation. One more time. You see that the noise figure, it depends on what? It depends on the amplification or the voltage amplification of the what? Sorry, the amplification of the what? Of the amplifier here, the GLNA. Clear? No response. Clear? Okay. Notice, by the way, when you plug in this equation, all of these G's are what? Are what? Are power gains. Are you following me or not? What we calculated here is a what? Is a voltage gain. So when you do the power gain, you need to what? You need to square it. Keep that in mind. Clear? Okay, good. So, this is a quick review from last time. You have this one in your notes. I just made a copy of it. Okay. Now, then we did the what? So, the first negative result is that by employing a shunt resistor, you resulted in reduction in gain. Then we did the what? The noise figure analysis. Let's review it quickly. In the noise figure analysis, always, we are going to always, there is no way in the final exam, I will give you what? A question which has the gate noise in it. Why? The analysis just takes longer. Are you following me? By the way, it's not harder, but it takes what? Longer. So it's a time-consuming thing. So the first assumption is that we are going to ignore the noise that is generated by what? The gate. We are also going to assume that all the noises are what? Uncorrelated, and because they are Gaussian, then they are what? Independent. By the way, that assumption is pretty okay. Why? Because this one is coming from the what? The source. This one is coming from the additional resistor, whereas the drain current is coming because of what? Because of the thermal noise resulting from the movement of electrons in the channel. Did you get my point or not? These are different sources, so making the assumption that they are uncorrelated is not out of the question. Okay, we represented each one of them, or it's equal to 4 KTBRS, 4 KTBR, and then the drain current is what is 4 KT gamma GDOB. Remember, what did we define GDO? GDO is the conductance when the voltage between the drain and the source is equal to what? Is equal to 0. Clear? No response. Clear? Question. What is the units? What is the units of GDO? Mo. Mo means what? 1 over ohm. Are you following me or not? Mo means what? 1 over ohm. Clear? Now, how did we define the noise factor? We defined the noise factor as the what? The total output noise power divided by what? The output noise power due to the what? Due to the source only. Clear? Question. How come the signal does not get in here? How come the signal power does not get into this definition? How did we define the noise factor earlier in the semester? We defined it as the signal to noise ratio at the output divided by what? The signal to noise ratio at the what? At the input. By the way, remember, this equation is true only assuming that we are operating at what? At room temperature. Keep that in mind. Yes? So how come the definition now is only noise? The definition is only noise because the signals will cancel out. There is only a factor of what? G, which is the gain. Yes? But that factor will be the same for both the noise and the what? Signal. So they will cancel out. I said it does not get into the picture. Clear? So we found out, we wrote the equation by superposition. And by the way, I broadcasted a typo here from last time. I think, where was the typo? I think this one was RS. This one was RS over what? Over R. Now, by the way, the effect of this mistake if we assume that we do have a power match is irrelevant. Why? Because the ratio is what? Is 1. But we need to be precise. Just because the ratio is 1 does not mean that it's correct. So it's RS over R, and this is the term here. And what did we see? We see that the noise figure is at least what? 2, which means at least how much dB? 3 dB. By the way, if we get to 3 dB from here, no way you will get to 3 dB from what? From this amplifier. From this amplifier. No way you will get to 3 dB. Are you following or not? By the way, if you get 8 dB also, you might be lucky. You probably get 10 dB or more because of this term. Did you get my point or not? Okay, good. Now, we then went into the second example. I don't want to go through it again. The second example has a what? Has a feedback resistor. This one more of a what? A wide band low noise amplifier rather than a what? Rather than the previous one. Clear? Oh, and we went through the analysis, same analysis. What did we found? We found that under certain condition, the AV, the voltage gain, ended up with what? Minus GM RL, which is the same as the common source with no what? With no feedback. What does that mean? It means that the fact that we do have a feedback in here resulted in what? No degradation in the gain of the amplifier. Clear? Clear? One more time. Why are we putting here if the gain did not change? And if this one is going to introduce noise, why are we putting it? If we do not put it, the input impedance will not be what? Real. Are you following or not? Will not be real. So it's not, I'm not going to be able to what? To match the source. Clear? So I calculated the input impedance and I found it to be equal to what? RF plus RL, 1 plus GM RL. Did you get this or not? Okay. Now, in reality, when you do the precise analysis of this one, you need to include the what? The CGS. You need to include the CGS. But what will you get is a what? Is a complex input impedance, which means it has a what? A real part and a what? An imaginary part. And you only take care of what? The real part. Did you get my point or not? Okay. However, in here we just simply ignored it. And we ended up with a what? We ended up with a noise figure. All of the derivations, same derivation. We ended up with a noise figure of this one. Now, in here, there is another typo. Please correct it in your notes. There is another typo. This one should be what? Gamma divided by what? Alpha GM times RS, where alpha is equal to what? GM over what? GDO. What is GM? One more time. What is the GM? GM is the transconductance of the transistor, which is what? Which is the partial derivative of the I with respect to what? VDS, when VGS is what? Is fixed on the saturation. Clear? Did you correct the typo? This one, it says what? Gamma GDO times RS. It should be what? Gamma alpha times GM RS, where alpha is what? GM GDO, which means what? The GM will not cancel. The GM will become what? GM square. This one will be on top. Clear? Clear? Okay. Now, in here also what we found that the noise figure can be dropped down if we assume what? If we take RF to be greater than RS and GM RS to be what? To be much, much greater than what? Much, much greater than 1. Clear? No response. Clear? By the way, if GMRS is much, much greater than 1, what can you tell me about this term? This term, just this term. Negligible or not negligible? Negligible. You follow me or not? So you end up with 1. And what can you tell me about RS and RF? If RF is greater than RS, can you tell me this one is negligible? This one is negligible, which means what? This middle term is gone, and you end up with what? 1 plus some term here. Clear? Which means what? The noise figure is better than the previous one because there is a what? There is a 1 here. In the previous one, there was a what? There was a 2. Clear? Okay. The third one, which we also went through before we ran out of time, and that is the what? That is the common gate amplifier. That is the common gate amplifier. Let me ask you a question first of all. Okay, that's the common gate amplifier. Where am I applying the input now? The input is now applied from where? From the source. The gate is what? Is grounded. Whenever you use, for example, when you say common gate, what does it mean? The gate is grounded. Common source, it means what? Source is grounded. Clear? This is a what? It's a common gate. And I applied the input in here. Now, what is the Zn? Zn is the impedance that you look between these 2 points. Are you following or not? This is the source. This is the impedance. By the way, this does not get into the picture when you do the AC analysis. This is for what? A DC bias. For AC analysis, what does this behave as? Short circuit. Just like what? Just like VDD. It behaves like a what? Short circuit. So this RL, do you see this RL? It will be, where is it? Sorry. This RL is what? RL. Yeah. Clear? Clear? Okay. So we wrote the equation again, relating the Bn and the In, and we divided one by the other. We got what? We got Zn equal to what? 1 over Gm plus J omega CGS. Again, what do you see in here? What do you see in here? That the CGS is available here. So unless, it's what am I saying here? Omega CGS is much, much less than what? Gm, which means what? I ignore this term, and what do I end up with? I end up with 1 over Gm. Is 1 over Gm real? Yes, it is real. If I choose 1 over Gm equal to what? R of S, this R of S here, then I have created a what? I have created the power match, the impedance match. Did you get my point or not? No response. Did you get my point or not? By the way, why didn't I put RS here? This RS. Why didn't I put it here? Because I was only interested in finding what? Zn. And the Zn is after the RS, not before the RS. Did you get my point or not? No response. Did you get my point or not? If you see this here, RS, I did not put the RS here. I don't care about the RS here. It's because I'm looking at what? The current is the same current. I'm looking at what? I'm looking at the Vn over what? Vn over In at this point here. Clear? Okay. Then we also calculated this again from last time, the noise figure. Did we reach this or we did not reach this? But in any case, this is the noise figure. I wanted to see what are the noise components. This is due to the what? Due to the source. You notice, by the way, the Vs, this Vs is gone. Why? I don't care about the Vs. This is just the noise. So this is now a what? A noiseless resistor, and this is the what? Equivalent, Thevenin equivalent noise voltage. Clear? As square, so it's a power, mean square. What is this one here? What is this? This is the drain current, which is what? Between the drain and the what? The source. You notice I want you to look at this one, and I want you to look at what? The directions here. Where is the directions in here? Here. The current is from the drain to the what? Source. In here, it's from the what? The drain to the what? To the source. Did you get my point or not? Yes or no? That's the I and D. Okay. Then I re-sketch this one. I want, first of all, to take the effect of what? To take the effect of the I and D. To take the effect of the I and D on the output. Where is the output? This is the output current. Where is the resistor, by the way? This is the resistor, the load. This is the resistor. By the way, in all of these analysis, what am I assuming? I am assuming that the load resistance does not introduce what? Noise. And in a minute, we will see that most of the time, actually, this load resistor, they replace it by a what? A tank circuit, a tune circuit. Did you get my point or not? Did you get my point or not? I will show you that in just a second. Let's not worry about it. I will show you that in just... question.
Yeah, the first circuit, RL should be on your right.
RL should be on the what?
On the right, the first circuit.
What first circuit? You mean this one?
Yes.
This one. This is the drain.
And RL will be...
RL will be, by the way, if this is the DC, remember there we are only talking about what? The noise. By the way, even this RL will not get into the analysis. You see, do you see RL in here? Why? I am only interested in the output noise. This output noise came from who? This, what is this equal to? It's equal to what? This I and D, yes? Plus what? The GMVGS. Did you get this or not? This R, in reality, it's where? It's between the drain. This is it, here. It's between the drain and the what? The VDD. Now, when you are dealing with what? AC analysis, that VDD becomes what? Ground. Which means what? This becomes like this. Clear? And in here, we are not dealing with signal analysis. We are dealing with noise analysis. And once you decided that the load resistance does not introduce noise, this irrelevant. Did you get my point or not? Look, by the way, look at the result. Do you see any RL in it? There is no RL in it. Did you get my point or not? Okay, good. Now, what do I need to calculate? I need to calculate the output what? The output noise power. The output noise power. Yes? Due to who? Due to who? I said the output noise power. I'm sorry. The output noise current due to who? Due to the I and D. How do I know that? How do I know that? Look what I did to the source. The source, this is the source connected to what? RS. Why is this one connected to the ground? Why is connected to the ground? Because I'm shorting this. I'm using the what? The superposition. Yes or no? No response. Okay, so good. So what is I-N-O, comma D? Do you understand the notation? What is the total noise output? What is it? It's I-N-O, comma D plus what? I-N-O, comma what? R-S, which is what? Which is the noise introduced by what? By the source resistance. The other one is trivial, which I'll show you in just a second. Let's look at this one first. So I-N-O-D equal to what? I-N-D plus what? GM-VGS. Now, what is VGS? Where is VGS? VGS is this voltage. VGS is this voltage. What is this voltage? This voltage, VGS, is this one, which is what? Minus I-N-D. I'll explain to you why the minus in just a second. I-N-D plus what? GM-VGS, yes? Plus what? J omega CGS VGS. Can you tell me what is this? J omega CGS VGS. VGS is this voltage. And I'm multiplying it by J omega CGS. What is this? There's the current in here. Did you get this or not? Okay. All of it multiplied by what? By RS. You get the voltage between what? Between the gate and the what? And the source, which is the VGS. Did you get my point or not? Yes or no? Okay. Why it's minus? It's because I'm assuming that this voltage, VGS, is what? Between the gate and the source. It's in the other direction. Did you get this or not? Okay. Now, from this equation, what do I get? I get VGS in terms of what? I and D. Did you get this or not? Yes or no? You are losing me? Are you losing me? Hey, are you losing me? Okay, good. Now, VGS in terms of I and D. What is my goal? My goal is to find this in terms of this only. I don't want this in here. So the VGS, I put it there. And I what? I substitute it in here. And then what do I get? I get this. Yes? And then I made the approximation. I want to get rid of the J omega axis. Sorry, the J omega term. So this one is gone. This one is gone. What do I end up with? I and D over what? 1 over what? 1 plus GMRS. Did you get this or not? Now, what do I need to do to this, by the way? What do I need to do? Now, first of all, let me make a word on this. To provide for power match, what did we found? We found that RS has to be equal to what? 1 over GM. Agree? Which means what? What is INOD? INOD, if this is GM is equal to 1 over RS, what is this? This is 1, which means what? IND over what? 2, which means what? It means half of the drain current is going where? To the load. Did you, when I say half of the drain current means what? Half of the drain noise current. This is a noise analysis. Did you get this or not? Half of it is going to go to the what? To the load. Clear? Okay. So, if power match, again, RS is only 1/2 of the drain noise current goes to the what? Output. Explain to me, where did this come from? Can you explain this one to me? INO, comma what? RS. What is this? What do I do to this, first of all? What do I do to this? Open circuit. Yes or no? What is the current will be? If you open this, what is the current will be? It's GM VGS. Yes? No response. Yes? So INO, comma, RS equal to. Now, what is the VGS? What is the VGS? Tell me, what is the VGS? The VGS is what? Is the voltage between this point and this point. Yes? But what is that? That's this voltage, which is what? VNS. Yes? Divided by what? RS plus what? RN. RN is the what? Is the impedance that you look at it this way. Did you lose me? You lost me. Did you lose me? You lost me. Okay, one more time. Concentrate. I want now to take the effect of this one. At the what? At the noise output current. The noise at the output. What do I do to this? Open. What is the voltage? What is the current this one will be? VGS. Do you agree? GM, VGS. Agree? But what is VGS? What is the voltage VGS? The voltage VGS is what? Is VNS, which is this, not square bar. I'm not talking about power. I'm talking about voltages. So it's what? VNS divided by what? RS plus what? RN. Yes? Which is what? What is this? RS plus what? RN. RN is the what? RN is what? Is the resistance looking at it this way? Are you following me or not? Okay. This is a current. VNS divided by what? RS plus RN. But this is also equal to what? GM divided by what? 1 plus GM RS times what? VNS. Can you tell me where this came from? Where did this come from? VNS over what? Times what? GM plus 1 plus GM RS. Where did this come from? This came from this fact. The ZN, where? No, sorry. Where did this come from? Ah, this one here. The one, if we ignore this term here, it becomes what? GM, the GM, remember, it's what? GM VGS. This GM is this. What is the VGS? The VGS is what? Is VNS over what? 1 plus what? GM RS. Did you get this or not? Yes or no? Okay. By the way, answer me the following question. How come this is this one? Can you explain to me this equation? This. What is this? Can you tell me what is this? Just this one. Just this one. What is VNS over RS plus RN? That's the input current. Do you understand that or not? The source, and the input current. Why is it the output current? Because the current gain is equal to what? 1. Did you get my point or not? This is a common gate. The current gain is equal to 1. So the output current is the same as the what? As the input current. And then I replaced what? I replaced the RS plus RN. I wrote it like what? VNS times what? GM over what? 1 plus GM times RS. Because I substituted for what? RN. What is the RN equal to? 1 over what? GM. Yes? So what do I get? GM goes on top. And then what do you have here? 1 plus GM times RS. Did you get it? Did you get it? Question?
Yeah, can this show the top of this page? Yeah, based on what we did that condition.
This one?
No, the value CGS, RS.
No, there's no condition. This, I wanted to make this one simple notation. There is no condition. By the way, we assumed what? We assumed that we are dealing with low frequencies. So here we are assuming that omega CGS RS is much less than what? Much less than 1. Did you get my point or not? This is just to get rid of what? Get rid of the J here, because the current happened to be a what? A phasor current. It's a complex current rather than a what? Rather than a real current. Did you get this or not? This is just an approximation. Clear? Did you understand this? Everybody? Did you understand only this? That's because the current gain is equal to what? 1. It's something in here in the Xerox machine did not go through. What should it says here? Current gain equal to what? What? Do you have it in your notes? Oh, I did not post this one already? I thought I already posted this one. Okay, anyway. Clear so far. Clear so far. Now the total noise power is what? The F is the what? Total noise power at the output divided by what? The total noise power, the noise power due to the what? Source. Explain to me where the 1 came from. 1, because there is a term here which is the same as this one. Yes? What remains? The output noise power due to what? Due to the current. Explain this one. Where did it come from? This one. Just the numerator. I just showed you that I, N, NO, D is this. What did I do? I square both sides and I took what? Average. Did you get it? Yes or no? So I get what? I square ND average, and then what? 1 plus GMRS, the whole thing square. Where did this come from? Same thing. This I and O, I square it, yes? And I took what? The average. And then what? I substitute the I and D square average and the VNS square average from the definitions. the 4KTB, and so on and so forth. I put it in there. This is what I get. This is what I get. Can you check also this equation at home, please, to see if I made a mistake in here or not? No, I'm probably not. Okay, but did you get it? What do you notice? What do you notice? Compare it again with the CS with resistive termination. How much was the F? It was this. How much is the F here? It's this. Did you get this or not? Which one is better? This one is better. Are you following me or not? The common gate is what? Is better. This one, they found out that they can reach what? With common gate, around 5 dB. Is that good or not so good? It's not so good. 5 dB is also not so good. But compared to the what? To the 10 dB and stuff, this is very good. Did you get my point or not? Yes or no? Okay. All the analysis, by the way, here, do you agree that it is straightforward but a little bit tedious? No, you don't agree? No agreement. No agreement. I thought you will agree. Okay, now for the most important architecture. This is the one that you will be asked upon. Clear? That's the one that we are interested in, which is called what? The source inductor. Sorry, inductor. Degenerated LNA. Don't sketch anything. Sorry, don't write anything. You just download it from the site after I posted here. Look what I did here. Look what we did in here. This is a common source. So back to the common source. I put an inductor in here with the source to the what? To the ground. Which means what? It is no longer a what? A common source. Because when you say common source, what does it mean? It means the source is what? Ground. But now the source is what? Is connected to LS. This LS, by the way, is a pretty small. Which means what? This is probably a parasitic inductor, a bond wire. Are you following me? This is relatively small. I added another inductor in here for a reason. That reason will be clear in just a second. For the time being, just what? Just accept it. Did you get this or not? Clear? And I called it what? LG. And then, of course, this is RS, and the VS, this is the source. Clear? Okay. Now, one more time, let's reiterate what are our goals. Our goals is to make what? The input impedance where? Looking from where? Not looking through the gate, but looking in here. Why? Because now this one became part of the whole thing. Did you get my point or not? This became part of the whole thing. So the Zn, do you see the Zn? Zn is looking in here. Clear? There's the equivalent circuit. Is the equivalent circuit clear? Notice, by the way, in this case, I left the what? The CGS here. This is the CGS. Clear so far? Okay. Help me with the equation. What do I want? I want to get the voltage in here at this point and the current passing through this. Why? So that when I divide the voltage times the current, what do I get? I get the Zn. And what do I want in this Zn? I want a real component. Are you following me or not? I want a real component. Let's see if you can help me here. What is the Vn? What is the voltage? It's I times what? J omega Lg, which is this one, J omega Lg, yes or no? Plus J omega Ls, which is the current here. Notice, by the way, the current that goes in here is not the same as the current that comes in here. Do you agree? However, is part of the current that comes in here, part of it, is it this one? So that's why I added it. But then I will leave the other term in here. Did you get my point or not? Okay. Where is this coming from? Can you explain to me this term? This is I times what? 1 over J omega CGS, which is this one. Did you get this or not? Can you explain to me where this came from? That's the GM VGS, this current, times what? J omega LS. Answer me the following question. This current plus this current, is it the same as the current that comes through LS? Yes, it is. So I separated them so that I can group them with this. Clear? Okay. Now, in this equation, how many unknowns do I have? I have the VI and the I and the VGS. I need to get rid of the VGS. Did you get my point? But what is the VGS? What is the VGS? VGS is this voltage. What is this voltage? It's the current times what? This impedance, which is what? I, this I, times what? 1 over j omega CGS. Clear? I will take this VGS and I plug it in terms of the I, and then I group the I together. This is what I get. I want you to tell me, what did I get in here? Did I get a real value or did I get a complex? Where is the complex? Sorry, where is the real value? Is there a real value? That's the real value. What am I going to do? I'm going to resonate those. At resonance frequency. At resonance frequency, what is this equal to? At resonance frequency,
the time is
what is
22
this
o'clock.
equal to? By the way, how does the circuit look like? I think you lost me here. Let me show you one thing so that you understand. Do you agree that the input circuit looks like this? Let's see. You lost me here. Please concentrate. Is this RS? Is this RS? Okay. LG, it became what? LG plus LS. Do we agree? Okay. Plus, what is this? VGS, which is this one. Sorry, CGS. I said VGS. CGS, which is this one. Yes? Where did this come from? GMLS over CGS. This term. Where did it come from? This is this term. The real part. Agree? What does this one look like? Just this one. What does it look to you? A resistance in series with a what? A capacitor. In series with a what? Inductor. This is it. Did you get it or not? And what is this? That's the original RS. Did you get my point or not? Okay. Will this one resonate? What is the resonance frequency? The resonance frequency, I know that omega naught is equal to what? 1 over square root of what? LC. Now, what is the L here? The L is the combination, which is what? LG plus what? LS. And the C is what? CGS. Did you get this or not? Yes or no? Okay. Now, when I resonate them at omega naught, what is this term equal to? This term equal to 0. What do I end up with? I end up with Z into be what? Real. Which means what? For power match, what do I put? RS equal to what? GM. LS over what? CGS. Oh, hold it. I need to make the comment before I answer a question. Please give me a minute. What did the LS decided? I mean, what was it used for? It was used to provide for what? The power match. Yes? Can you tell me why do I need the LG? This LG. First of all, can I remove it? Can I remove this LG and will it still work? In other words, what will this one be? It will become omega naught equal to what? 1 over square root of what? LS CGS. Do you agree? Then why did I put it? I put it to get what? 2 degrees of freedom. If you put only LS, that LS is going to be used for power matching and for determining what? The resonance frequency. Did you get my point or not? I wanted to separate those. In here, by the way, which L is going to determine the fundamental frequency or the resonance frequency? It's the LG, because the LS is much smaller than what? The LG. So the LG is going to be used to control what? The value of omega naught. Yes or no? And the LS will be used to what? The LS will be used to what? For impedance matching, for the power matching. Did you get this or not? Yes or no? If you use only one inductor, then you only have what? One LS to control. Clear? Okay, what is your question?
Yeah, I mean, this circuit will only be working on the resonance frequency to be...
Which means what, by the way? What does that tell you? What kind of an LNA is this? Is it a wide band or is it a narrow band? That's a narrow band. Why? Because this only occurs at what? At what frequency? At one frequency. Are you following me or not? Now, listen to me. If this one is not equal to 0, if this one is not equal to 0, can I still introduce an impedance matching circuit to match it to a what? To a real resistance? Why? Because at least I got a what? A real part. That's the important thing. I need to get a what? A real part to be able to what? To match it to a what? To a real resistance. This one here can be lumped with the what? With the L shape or with the pi shape or with the T shape, whatever the case might be.
But the noise figure will increase because
The what?
noise figure will increase.
The noise figure might not increase if you introduce a circuit which is what? A purely LC. You follow me or not? Now, this is theoretically speaking. In reality, you are going to have what? Some parasitic or some internal resistances inside those inductor and capacitor, which will introduce what? Which will introduce the noise. Additional noise. But I mean, theoretically speaking, it should not have any effect on the noise figure because it's not a resistive element. Capacitive.
The gain of the amplifier will be perform badly if
Actually, the gain will increase. I will show you that because we have a resonance circuit here. Can you hold a second? Please, just hold a second first. Did you follow the analysis so far? Yes or no? Did you understand why do we use LG? Yeah, to get what? To get 2 degrees of freedom. Freedom in choosing what? Omega naught? By the way, is omega naught given in the problem? What do you mean no? Omega naught is going to be given in the problem. The question will tell you what? Design a low noise amplifier at what? At that frequency. It's given in the problem. What? The question will not tell you design an LNA and that's it. At the frequency will be given. Yes? From it, what are you going to do? You are going to figure out what LG is, not what LS. LS is small. LS you will figure it out from here. Clear? What is given here? The RS is given, yes, or usually 50 or 70 ohm, whatever, 75 ohm, and from it you can figure out what the LS requires. Clear? Okay, good. Now, let's get back to the circuit so that we can see the gain stuff here. Let's get back to the circuit here. This is the equivalent circuit. Now, remember one thing. Listen to me. Where is the G? Where is the gate? This is now the gate. And this is now what? The ground. So that's the VGS. You might say, but Professor, the source is not grounded. We already took the effect of this in here. That's why I added this. Yes? Okay. At resonance, this one and this one, the voltage across them is equal to what? 0. Do we agree? But the voltage across the capacitor only is not equal to 0. Actually, it is what? Much higher than the input voltage. Did we study this earlier or not? We studied this earlier when we were reviewing the RLC circuit, and we referred to it as a what? A Q boosting mechanism. Q boosting. What is the voltage across the capacitor? Across the capacitor voltage is what? Is VGS, which is equal to what? Q over times what? VS. Did you get my point or not? You are losing me? You lost me here. What is the Q of this guy? Can you tell me what is the Q of this guy? Is this a series circuit? Series circuit. What is the Q? Q is what? For a series circuit is what? Is omega naught L over what? R, or what? 1 over omega naught CR. Do you remember those? And let's use the L. So it's what? Omega naught LG plus LS over what? R. What is the R? Is RS plus what? GM, LS, CGS. Notice, by the way, if we are doing a power match, what is this equal to? This will be equal to this one. Yes? So the denominator will just simply be what? To RS. That's this one. Did you get this or not? Yeah? Huh?
Why is there CGS at question 6?
CGS at question 6. Or at equation 6.
Didn't we, approximately say that GMLS over CGS equal RS?
No, this is the other way of writing it. The L is gone. The Q, remember, one more time. For a series circuit, what is the Q? Omega naught. L over what? Or? So this is the other way of writing it. Clear? Okay, good. Now, see, there is no L in here. So you either write it in terms of the what? Of the C, or in terms of the what? Of the L. Clear? Okay. Now, what is this? We refer to it one more time. We refer to this as what? As a Q boosting. What is the Q boosting? One more time. The voltage across the capacitor at resonance, we are talking about at resonance. The voltage in here is much higher than the voltage in here. Clear? That's one of the things that you need to be careful when you design this type of low noise amplifier, because the input to the amplifier might what? The input to the device itself, which is the what? Which is the gate, might go what? Might go very high. Did you understand that or not? And might result in what? You lost me here. I think you lost me. What is the characteristics of the device? The output characteristics is ID versus what? VDS for what? Constant VGS. Yes? That VGS is going to be what? Q times as high as this one. Which means the beauty of this one is that I need to make sure that the voltage here does not have a large what? Swing. Why? Because if it is a large swing, it's already going to be boosted by what? By Q. Do you understand that or not? And it might result in what? Breaking the device itself. Clear? Luckily for us, the signal in here is weak. Do we agree? Why? This is the received signal. At the receiver here is weak signal, which means what? The peak to peak is very little. Clear? No response. Clear? So we have the Q. VGS is equal to what? Q times what? VS, which means the voltage gain, the amplifier voltage gain, which is what? V naught over VS. Now, what is the V naught? Let's see if you can tell me. GM, what is the GM? Explain to me, where did this come from? Can you explain to me where this came from? Still waiting. Still waiting. Where is the equivalent circuit? 1 second. Yeah, this is where is it? What is the current in here? The current in here is minus GM VGS. Yes? No response. Yes? No response. Okay, and what is VGS? Q times what? VS. So what is V naught? What is V naught here? The V naught is what? Is I need to show you one thing at two steps at a time. Okay, let me show it to you. What do I have? I have V naught equal to what? Minus GM VGS times what? R. And what is VGS? Minus GM. What is VGS? Is Q times what? Agree? No response. Agree? So what do I have? What do I have? At V naught divided by what? VS equal to what? Minus GM. Sorry, minus Q GM times what? R. Huh? You lost me?
What's V naught? Is it the voltage at RL?
Which one?
V naught.
V naught is the voltage at the output. Yes, it is the voltage across RL. And this is RL. Where is here? And the what is the current, by the way, here? It's minus GM VGS. And what is VGS? VGS is what? Is QVS. Clear? So I ended up with what? AV, which is equal to what? Now, Q times GM, I am designating it by what? Capital GM. This is the what? This is, don't confuse this with this. What is GM? GM, the transconductance of the device. Whereas GM, capital GM, is the transconductance of who? Of the amplifier, the whole amplifier. Did you get this or not? And you see that it what? That the gain is what is going to be, because GM is what? Is Q times GM. Clear? No response. Clear? Yes or no? Okay, good. Now, the noise figure analysis. Did you understand the power matching? Yes? And the gain? Okay. Now, the noise figure analysis. Again, by the same token, we are going to say what? F is the total noise power at the output divided by the noise power at the output due to the what? Due to the source. So again, I write the equation. Are you familiar with this equation? What is this due to? It's due to the RS. What is this due? Drain current. And this is just due to the what? R. This is 1 over this. Now, what do I need to find? I need to find this term, and I need to find this term. Let's start with this term, because this one is easier. What is VNO, comma, RS, square bar? First of all, explain to me what is this in word. That's the what? The mean square voltage of the noise at the output due to what? Due to the source. What is it? It's VN square RS bar. What is this? Can you tell me what is this? That's the mean square value of the noise due to the what? Source. Where? At the input. And what am I multiplying it by? GM square or L square. Where did this come from? This is the square root of this guy. Did I say square root? A square. It's the square of this guy. Yes or no? Oh. Now, did we understand this? And this is equal to what? 4 KT RSB. What is this? 4 KT RSB is this guy. Yes? Times what? GM square or L square. Did you get it? Okay. Now, what is this equal to? What is this equal to? Explain to me, where did this come from? Where is the circuit? Here. What am I going to do? What am I going to do to the noise source? To the noise. I'm going to short circuit. Yes? What is the current at the output? Due to the what? Due to the drain current. Yes or no? What is it? It's I. In other words, V NO square ID bar equal to. Did you get where this came from? You are struggling. You are not getting where this came from? What is this? Can you tell me this in words? The output noise power due to who? Due to the drain current. Yes? Forget about the square and forget about the average. Just look at the remaining. What is it? The noise voltage at the output due to the what? Drain. What is it about? This is the noise voltage at the output. So it's what? I N D. By the way, you don't even need to write GMBGS. You can write what? I N D square times what? RL square. Did you get this or not? Notice, by the way, in reality, there is a minus sign, but when you square, it becomes positive. Now, this is what? Is 4KT gamma GB. This gamma is what? Sorry, this G is what? GDO. Times what? Times RL square. Clear? No response. No response. Clear? Okay. Now, what is this? Let me write it down. This is RG over what? RS plus gamma over alpha GM times what? Omega naught over what? Omega T, the whole thing what? Square. Clear? No response. Clear? Do you remember what omega T is? What is omega T? Still waiting. It's GM over what? Clear? Clear? Do you remember how did we define this in words? That's the what? That is defined as the threshold frequency when the current gain equal to what? Equal to 1. Clear? Okay. Now, and you can see that as F, by the way, you can also write it in terms of the Q. You will see that the F goes 1 as the Q square goes what? Goes up. Q square goes up. Q square is being what? Is being, this, by the way, you can write it in terms of Q square. Clear? No response. Clear? Okay, how come nobody said where this omega naught came from? This one here. Omega naught, you can write it in terms of what? Q. So this one will be a function of what? Of Q. And you will see that the Q will be in the denominator. Did you lose me? You lost me again. What is the omega naught here? What is the value of omega naught here equal to? 1 over what? 2q RSCGS. Yes? Okay. But in here I have what? Omega naught square. Which means in the denominator, what do I have? I have a term that has what? Q square in the denominator. Agree? What does that tell you? It tells you that the noise figure will go what? Will go down as the Q square goes what? Up. Did you get this or not? But on what expense? On the expense that there will be a danger as far as the linearity is concerned. Why? You lost me again? Are you losing me? Why is there a danger about the linearity stuff? The input voltage becomes what? High. And the input voltage becomes high, it might drive the amplifier into what? Into the saturation stuff. Clear? No response. Clear? Okay. The Q, by the way, you can control the value of the Q through who? Where is the Q? Through who? Through LG. Why? Because LS is relatively small. Are you following me? So through LG, you can control the value of Q. Clear? No response. Clear? Okay. Now, the performance is much better than the what? Than the previous one. Now, let's look at the entire design, the overall design, which is this one. Let's see if you can help me here. What did we do here and why did we do it? Let's see if you can help me. In the previous case, how many transistors did we use? We have only one transistor. But all of these circuits that I was showing you here did not show you any what? Biasing. The biasing was left out because we were only interested in the what? In the AC analysis or the what? The noise analysis. Clear? Okay. Let's see if you can help me understand this design. Do not worry about these first. Do you understand the M1 and the LS? This is what we just did. This is the LG. Did you get it? Okay. The CB is what? It's just a blocking capacitor. Why? Because I want the input to be what? To be the AC, the pure RF. Did you get this or not? For RF, what is this behaving as? That's behaving as a short circuit. Did you get my point or not? Okay. Now, what other changes did we do? What other changes? I want you to look at this diagram and tell me what did I do. I replaced, first of all, the RL by a tank circuit. Did you get this or not? Yes or no? This tank circuit, I am going to tune it at what? At omega naught. Did you get my point or not? By the way, I can even tune it to a different frequency, allowing the output to have what? To have two peaks. Did you understand what I just said or not? No, you lost me here. I can tell you lost me. Do you see what did I do with RL here? What did I do with RL? I replaced it by a what? Tank circuit. Why? Why? This one does not introduce what? Noise. Assuming idea. This one doesn't introduce noise. It introduced noise. I just happened to what? Ignore it. Did you get my point or not? In the analysis, I just happened to ignore that noise. Clear? Okay. So what do I have? I replace it by a what? A tank circuit. Now, if I want the output frequency to be the same as the input frequency, in other words, the tuning to be the same, which means what? You are enhancing the gain, because both the input and the output are tuned circuit. Then you set what? You set omega naught equal to what? No, this one is incorrect. It should be what? Square root, right? Yeah, there's square root. I'm sorry. You agree or not? Yes? No response. Could I have just replaced this one by a what? A tank circuit? Why did I add this transistor? Do you see this transistor? And what do we call this transistor? We call it a cascode. Did you take electronics classes? Yes? Never? Not heard about it? M2 is called a what? A cascode. For what reason? What is the reason for the, by the way, is it a common gate? Is this one a common gate? Yes, it is. Why? Because in AC, the gate is what? Is grounded. Yes? which means what? What is the current gain in here? 1. This one will not provide you with a current gain. Did you get my point or not? But why are we using it? Why can't we put the tank circuit in here like this? In other words, replace this R by a tank circuit. Still waiting. Did you take cascode in previous electronic classes? Never? Never? Huh? I cannot hear you. It provides isolation if this one is resonant to the same frequency as the input. There is a capacitive element between the drain and the what? Gate. A capacitive element, which means that there might be a what? A leakage from the output to the what? Input. So, what if there is a leakage? So, what is the problem with that? The problem with that is that if you do have the amplifier like this, this is the LNA. Remember, the LNA will be followed by a what? The mixer. And if we do have what? Leakage from this guy to this guy, there is a possibility that what? That this local oscillator will what? Leak. Are you following me or not? All the way to the what? Antenna. Now for what? For the super heterodyne, this is not a big deal. Why? Because in a super heterodyne, the local oscillator is not the same as the what? The RF. But for the homodyne, is it a big deal? It is a big deal. Now, let's assume this one is different. Is isolation is still a big deal. Why? Because this one might go to the antenna and it will interfere with what? The people who are operating in the adjacent channels. Did you lose me? Yes or no? Yes or no? What do we call this phenomenon? Isolate. If we do not isolate from the output to the input, what do we call this? Anyway, that's the Miller effect. Are you familiar with the Miller capacitance? Where? Which course? It's a Miller capacitance between the what? Between the output and the what? And the input will depend on what? Will depend on the gain. Did you get my point or not? And as the capacitance goes higher, what does it mean? 1 over j omega c gs becomes what? Lower, which means it is behaving as a what? You are losing. It's behaving as a short. Did you get my point or not? Which means what? The output will be what? will be fed back to the input. Did you get this or not?
If there is a leakage from the output of the amplifier to the input, will this drive the amplifier to the nonlinear region?
No, this is not again, as I told you, the question is not leakage from the output. We are worried about the leakage from the mixer to the what? From the mixer to the what? From the local oscillator. I said the mixer, I'm sorry. From the local oscillator to the what? The amplifier is like this. If there is a leakage between this one and this one, and if there is a leakage between this one and this one will be like this. Leakage from here, and this one will leak back to here. That's the problem. Did you get my point or not? Why don't you wait until we get to the mixer, and then I will bring it to you again, so that you can see it clearly. Clear? Okay. This is called the cascode. Now, are you following me so far or not? Okay. Now, what is this? Can you explain to me this? This portion. That's the biasing. Are you following me or not? That's the biasing, this biasing. Now, what do I call this? The biasing here forms what is known as a current mirror. Do we know what a current mirror is? Have we taken it in different classes? Which one? 539? 479. If you take 479, by the way, those of you who have not taken any courses in electronics, I would recommend in the summer, if you don't have better things to do, I would recommend that you sit in Professor Choma's class on 479. And when he teaches it in a marvelous way, the electronics design. You follow me or not? Don't take it for credit. If you tell me, Professor, I have already exhausted all of my 400 level allocation, which is 3 classes, just sit in the class. He is generous. He's not going to tell you, leave the class. I do advise you strongly to sit in the class if you want to take future electronic classes, analog circuit design and stuff like that. Clear? No, nobody was enthusiastic. Did you take 479? Yeah, so you, who, with Professor Choma?
No.
Who? Oh, different professor. But what I'm trying to tell you is that if you take it with a Professor Choma, it's a totally different experience. It's totally, huh? 536? Yeah, it's a different experience with Professor Choma. It's a different experience totally. So I really do advise you, even if you cannot take the class, sit in the class. Listen. Now, let's get back to here right now. What is the purpose of this? Can you tell me what is the purpose of this? The purpose of this is that through biasing of this guy, I can make the current in here the same as the current in here. And I want this one to be what? Constant current. Did you get this or not? And that's why they call it a what? A current mirror with M1. M3 is the current mirror of what? M1. What does a current mirror means? A current mirror means what? Biasing one transistor with a constant current that is controlled by who? By a voltage on a different current. On a different transistor. Did you get this or not? We are trying to control the current that goes in here from what? From controlling the biasing of what? Of this guy. The biasing, of course, is through R bias and the R. This R bias, you need to be careful in choosing it because this bias will also introduce what? Will also introduce noise. Are you following or not? Will also introduce noise. So you need to be what? You need to take it large enough, but not too large to introduce what? Noises of its own. Clear so far? Yes or no? Did you understand why cascode is needed? Do you understand why is this one needed? This one is needed so that you can control the biasing current of this guy by what? By controlling it here. These and this are the mirror image of each other. Clear? Clear? Okay. Now, there is one more thing that I need to show you. Here, by the way, definition of the current mirror, you can read it. There is one more thing I need to show you before I leave the LNA, which is the following. All of these, by the way, if you can see how many, oh, by the way, the charts, let's see if we miss anything in the chart. This is all the common gate. We already talked about it. The noise figure of the common gate, the drain contribution. This is all the common gate. This is the comparison between them. And then this is the inductive source generation. We covered all of these things. Very clear. But the equations, I derived it here or again. This is the equation that we just derived. You remember this? We just derived this one here. Now, and this is the voltage gain. I just showed you this. Remember, you get the boosting. Okay. Now, but I want to show you, this is, by the way, the cascode narrowband LNA. This is the one that I just showed you. This is the cascode. This is the what? This is our inductor degenerated, and this is the load tank. But this one will give you only one output. Are you following me or not? We will see when we get to the mixer in a minute. We will see that if we want a double balanced mixer, which we don't know what that means yet, I'll explain to you. You might need to have what is known as a what? A differential, CSLNA. What is a differential? By the way, this is called what? Single-sided. This is the one that we just talked about, the single-sided. Why do we call it, sorry, single-ended? Why do we call it single-ended? We have only one transistor and we are taking the output from the drain. Did you get, remember, sorry, drain from the cascode. This is just a cascode here. Did you get my point or not? Okay. I want you to tell me what is the difference between this one and this one. Don't look at this one here. I want you to look at this one. I'm using what? 2 transistors. Clear? In a differential pair. And where is the out? You notice, by the way, they are equivalent in the design. See this one? This one is the load of this guy. This one is the load of this guy. Are you following me or not? Oh, and where am I taking the output? By the way, what is this? When I connect, what is this one and this one behaving as? Those are the cascode. Did you get my point or not? Yes or no? These are the cascode. And what is this? This is the biasing. It's a common what? Common gate. Yes? This is the load. Where am I taking the output? I'm taking the output, the difference between these two. This is what is known as what? Differential output. Whereas in here, where am I taking the output? I'm taking the output in here. We call it a what? A single-ended. Clear? Now, when you do have a differential output, the inputs, do you see the inputs? By the way, you can either design it this way, or you can look at it this way. Let me show it to you. Do you see what? Can you zoom into place a little bit? You see this? This transistor and this transistor are these. This one and this one. Yes? And they are driven by voltages of what? Opposite polarity. This is positive. This is what? Negative. Now remember, when this is positive, what does it mean? It means all the current will come what? That way. And none of the current will come what? This way. Why? Because this one will be what? Cut off when this one is negative. Did you get my point or not? Okay. How about the other way around? In the other cycle. The input is a sinusoid, which means what? Half positive, half negative. On the other cycle, what can you tell me about this? Cut off. This one is what? Conducting. Yes? Okay. You can bias the code such that the current will be steered all the way, either here or what? Here. By the way, is this a constant current? That's a constant current, a saturation current. Yes? How do I control this current? I control this current from the what? From the current image. You lost me here. Did you lose me? You lost me. Where is the chance? I control the current in here from here. Yes? Okay. This is controlling this current. Constant current. Saturation. Saturation. Yes or no? Okay. You control. Remember, how do you control the current in a transistor? You control it through biasing. You follow me or not? But in this case, you are biasing the what? A different transistor, but the current will be what? Will be the same as this guy. Clear? Okay. And this is what? This is LS, LS1, LS2, or LS1, LS2. These are these. This one and this one. And here I wrote what? LS2, LS1. You could connect them together. Clear? Okay. And this one here. Now, the voltage, when you take it from here, it's a what? It's a differential voltage. When we get to the mixer, we will see that most popular mixers do what? Do use differential. Local oscillator and differential what? RF. Yes? If we need differential RF in the mixer stage, what do I need to use? I need to use the LNA as a what? As a differential. Did you get this or not? Yes or no? But I will show you that when we get to the mixer. Right now, I'm not sure you are following me here. Now, the gentleman's question is the following. Why can't we use what is known as a balun? First of all, let me define the word for you. A balun Sometimes, by the way, they call it balloon, but it's not a balloon. You know that. It's not a balloon. They call it a balloon. What does it stand for, by the way? What does it stand for? Don't tell me a balloon. What does it stand for? It stands for balanced to what? Unbalanced. Clear? Okay, let me show you the circuit so that you can see. Here, this will be grounding. Here, what am I taking? Here, is this the balanced or the unbalanced? From here, if I want to look at it from here, that's the balanced. Did you say there or not? Balance means what? Negative and what? Positive. Yes? Here, what am I looking at? Unbalanced means what? Means a voltage with respect to who? With respect to the ground. Whereas in here, there is no ground. So I use what? Positive and what? Negative. Of course, you can use that at the input. To change what? To change a single-ended to a what? Double-ended. Which means what? You take the input in here from the what? The single-ended low-noise amplifier, and you take the outputs from here to drive the what? To drive the differential mixer.
Professor?
Yes.
5 minutes left. Okay. Just heads up.
Did you get it? No, what do you mean before the LNA? LNA, yes. No, you could get the single LNA. In other words, you could design the single LNA, yes, and then the output will be converted to what? To differential. But in the other case, when you put this one, the input to the LNA, it means you want to design the LNA as a differential LNA. Oh, this is your question. I thought you are asking where should I put. Remember, by the way, when you do the LNA, differential NLA, any common mode interference or noise, common mode, do you understand what common mode means? Common mode means what? On this side and on this side will be what? Will be canceled out, will be rejected, which means what? It means that the linearity situation of the transistor, of the amplifier will become a little bit what? Better. Are you following me or not? You are getting rid of any common mode signals. However, you need to understand one thing, is that when you design your amplifier as a differential pair, it first of all will take more space. And there will be also more power dissipation because you are using what? You are using 2 transistors instead of 1. So all of these needs to be what? Needs to be traded. Are you following me? Now, some designs use what? Most of the time, the balloon, they put it what? If you decided to use LNA, just a single-ended LNA, the balloon will be inserted where? It will be inserted at the output. Do you follow me or not? Now, it all also depends on your design of the mixer. If you decided that your mixer is single-balanced, which is what? Good enough. If you say that is good enough, then you don't need a differential input. Clear? It will become clearer when we get to the mixer. Can you be patient for 2 minutes? Actually, it's more than 2 minutes. It's still next week. But did you get the idea? Did you get the idea? Okay. Another issue, by the way, that you need also to take care of is the following. When you connect this one to the ground and you connect this one also to the ground, you need to understand that there's a possibility that this ground and this ground is not the same value. Did you understand what I just said or not? Why? Didn't we see in the transmission line, just because we have a transmission line does not mean that the voltage at one point and the voltage at another point will be equal to the same thing? Because we cannot treat it as a what? As a lumped parameter circuit. We need to treat it as a what? As a distributed thing. So in here you need also to be careful to figure out what? To be able to figure out this. But if you use this, it doesn't matter. Do you agree with me or not? If you use this one, it doesn't matter. Why? Because these are what? Common mode signals. They will be cancelled by what? By this differential pair. So the differential circuits avoid the parasitic in the ground loop and modulation by other stages. Also common mode disturbances are whatever rejected due to symmetry and so on. So Double gain, better linearity for the same output level, but what? A double power, double area, and so on and so forth. Clear? Everything will be what? Will be double. Clear? Clear? Okay, good. Now, let's get into the next stage, which is the mixer. Now, let's first of all talk a little bit. I have only 1 minute left or 2 minutes left. First of all, question, very quick question. A mixer, is it a 2-port device or a 3-port device? 3-port device. Are you following me on that? One port is the RF. The other port is the local oscillator. The third port is what? Is the IF. Where is that? That's at the transmit. Oops. That's at the receiver side. And we call it a what? A down converter. On the transmitter side is the what? Is the other way around. Clear? The inputs are what? Are the IF and the local, and the output is the what? Is the RF. Clear? Question. Is it a linear device? No, it's not a linear device. Right away, we know that it's not a linear device. Why? Because new frequency components are being what? Generated. Which means what? In order to design a mixer, what do I need? I need either a nonlinear circuit or I need a what? A time-varying circuit. Time-varying circuit means what? Switching circuit. The impulse response is changing with time. Did you get this or not? Time-varying circuit or what? Nonlinear circuit. Clear? And we will study both, the design of both of them next time. Clear? No response. Clear? Okay. So the mixer, again, is an up conversion at the transmitter side. It's a down conversion at the what? At the receiver side. Fundamentally, it is just a what? A multiplication. So the V out, what is this? Can you tell me what is this? This is the RF signal with amplitude modulation and phase modulation. One more time. This is the RF signal with amplitude modulation and phase modulation. I am multiplying it by what? A pure local oscillator. It's a cosine. Pure local oscillator. When you multiply these trigonometry, what do you get? The modulation is still intact, both in the amplitude and in the what? The phase. But instead of being centered around omega LO, it is now centered around what? Omega IF. Clear?
Yes, sir.
And again, remember, the LO could be a high side injection or a what? Low side injection that we studied earlier in the semester. But I think I ran out of time. Did I run out of time?
Yeah, I'm just...
Okay.
Just
And
about.
next time we'll continue. Clear?
And this concludes EE 544 on Thursday, April 10th, 2014.